In this video, I will talk about stochastic modeling, in particular Bayesian updating, as a part of the course on machine learning and models for decision making in the Master of Civil Engineering at the Universitat Politècnica de Catalunya. Bayesian updating is basically a part of the general topic on uncertainty quantification, which is the science of the quantification of uncertainties in real-world applications. The purpose of uncertainty quantification is to reduce uncertainties in this application. So the purpose basically is the reduction of uncertainties in real world applications. So assume that you have a system. So you have a system that you want to study, and some aspects of this system, some aspects are not exactly known. So due to the lack of our knowledge, or the thing that we don't know about the system, some aspects basically, or some parameters, for example, are not exactly known. So we don't have a full knowledge of these aspects. And then because of this, we have some uncertainties, or we produce some uncertainties as the outcome of the system. So the outcomes are not certain. The goal is to answer this question: how certain are the outcomes? So the decision, our decision on the outcome of the system is basically based on the uncertainties, or the level of uncertainties that we produce in the outcome. If we have a high level of uncertainties, then we cannot trust the outcomes, or we cannot rely on these outcomes. So the study of this is the part of the uncertainty quantification. A typical example basically is a car accident. So assume that you have a car which is which has the same model, and it has the same speed, and it has also same road and environmental conditions. And then you have an accident, and then you have another car with the same properties that I mentioned, and then you have exactly the same accident, but the result of this accident basically is different results. Why? Because there are some small manufacturing differences. When you manufacture a car, for sure you will have different parts, very small different parts and differences in the manufacturing of the car. And then because of these differences, we produce slightly different results every time that we have accidents. So how certain are the outcomes of this accident is basically the purpose of this uncertainty quantification. And our decision basically on the outcome of the system is based on this. So there are two types of uncertainty quantification. Basically, one we call it forward, and another one is the inverse. And there are some methodologies for these two types, for the forward and inverse. The Bayesian updating that I discuss in this video is a part of the inverse quantification, uncertainty quantification. I will talk briefly about also forward techniques, but We will focus on these forward techniques in the next videos when we talk about stochastic finite element modeling. And all of these models is basically the part of the stochastic modeling topic. And for more details on this uncertainty quantification, I also recommend that you take a look at this Wikipedia page on this topic. As I mentioned before, in many applications, our decision is based on the outcome of the system. And when we are talking about uncertainty in the input, then we are considering, or we are interested in the stochastic outcome, because we know that also the outcome is uncertain. So in this framework, we assume that the input uncertainty is well known or well characterized. So it means that we know everything about the input, and we are not concerning about the input and the uncertainties because we know everything. And we assume also a forward propagation as an effective method to analyze the output. So an example of forward propagation is the stochastic finite element, which we will discuss in the next videos. So assuming that, then our decision basically is taken by analyzing the uncertain outcome. So I will give you a graphical representation of this. Basically, assume that you have a system and you have an input for this system, and you know everything about the input, including the uncertainty. So known uncertainty. So for example, if you have a parameter as an input, you know that your parameter has an average of mu with a standard deviation of sigma, and it has a probability distribution, for example, like this. Okay, and you know everything. You know sigma, you know mu, so you know everything about the uncertainty of the input. Then you want to find the uncertainty of the output or analyze it. So basically, you have another probability distribution. You want to find this probability distribution, and of course the mean and the standard deviation of the output. So I put sigma star and mu star for the output. So basically the goal is to find the mean and the standard deviation. So this process, basically we call it forward propagation, and in summary, forward propagation is going from the input, knowing the input, to analyze the output. Another example is the analyzing the design. For example, you have a design and then you want to see that this design is acceptable or not. So this decision is basically based on analyzing the output, which is the failure of this design, and then you want to find the probability of that failure. So if you analyze the probability of that failure, then this is another example of the forward propagation. On the other hand, in the inverse problems, we are going through the inverse direction. So basically we are going from the output and we are analyzing the input. So in this framework, we have some data on the output, and based on this data, we want to find the best input or the parameters of our model that best represent the data. So this framework is also called model updating or data assimilation, and basically here we use data from the output of the model or the system to enrich, update, or improve the model. So assume that you have some data on the output and then you want to find what kind of parameters best represent this data or produce this data using that model. So as I mentioned, we have basically two problems: inverse problem and the forward problem. In the forward one, we are going from parameters as inputs to output as solution, and in the inverse problems, given some data which are the output, we are going to identify parameters. So when we identify parameters, basically we call this parameter identification. So a schematic of this is you have again input, and you have a model or system, so let's call it model, and then you have some output. So here in the model we call this input, for example, as parameters, and the output solution. So this direction, basically when you have your parameters and then you want to analyze the output, this is forward. And then when you have some data on the solution, and then you are going to identify these parameters, basically this is inverse. And one of the main methods or approaches for the inverse problems are Bayesian approach that I will discuss in the next slides. The Bayesian approach is based on the Bayes theorem, which is a consequence of conditional probability. So before presenting the Bayes theorem, let's introduce this conditional probability. Basically, this probability is the finding a probability of event A condition or given event B. So this bar symbol basically means given, and on the right hand side is the condition or the event that we know, or the event that has occurred. So this is why we call it conditional probability. And this probability is basically calculated as finding the joint probability. Basically, this is the joint probability. And this joint probability means that the probability of both event A and B occurs at the same time. And this joint probability divided by the probability of event B that we know. So let me give you an example. Let's assume that we want to find the probability of meeting a smart person, given that or knowing that he is a male. So you see here we have a condition that he is a male, and this probability basically reads as this. So P of probability of finding a smart person given, so this is given, or knowing that he's a male. So on the right hand side we have the condition that we have. So this basically, from this formulation, can be written as this, the joint probability. So this is again joint, and this is basically the probability of the male, which is the denominator. So probability of a smart and a male person is basically the number of the male and a smart person divided by the total number of people. So this is the probability of the first part divided by the probability of male, which is the number of the male divided by the number of people. So since the number of people in the numerator and denominator is the same, we can remove it from both terms, and we finally have this expression as this probability. So basically you count the number of smart and male people in the population and divide it by the total number of the male in that population, and then you find this conditional probability. A consequence of this conditional probability that I introduced in the previous slide is the Bayes theorem. Basically, in the Bayes theorem, we can write the probability of A given B as a function of its reverse. So its reverse is probability of B given A. So this is basically the reverse of this. And in this theorem, basically we can relate these two reverse probabilities by this expression. So how can we come up with this theorem from conditional probability? Basically, if we write PB given A, again a conditional probability of B given A, then this is again the joint probability divided here by PA. And then if we call this number one conditional probability and the second conditional probability, basically by merging these two, we can come up with the Bayes theory. This theorem was proposed by the British statistician Thomas Bayes at the beginning of 18th century. As I mentioned before, we can interpret Bayes theorem as information updating. So how this information updating actually occurs through this theorem. So first, let me name different terms in the Bayes theorem. So on the right hand side, this PA, basically we call it prior probability. This is the standard name for this term. But the interpretation of this term is the old information that we have, or initial assumption. So we start with some initial assumption, and then we want to update this initial assumption based on the new information that we receive. So sometimes also we have some old information, and then we want to update also that. So basically the interpretation of this term is these two expressions. This one, this PB condition to A, this is the new information that we introduce, new information. And commonly they call this term likelihood. This is again the standard name for this term, but basically the interpretation is the new information that we introduce to the system. So on the left hand side, we have the product of this new information multiplied by the old one, and then we call this a posteriori probability or updated probability. So this is basically updated information. So you see that on the right hand side we have a product of the old information updated by the new one, the likelihood, and then on the left hand side the outcome of this theorem is the updated information. So the denominator basically here, PB, we call it evidence. So this is basically takes the role of normalization. This term ensures that this posteriori probability sums to 1 for all the possible events. So basically here we call A as an event and B as an experiment, because we are doing some experiments to update our information. So this is why we call B an experiment given the event A. Let me give you an example on how we can use Bayes theorem for information updating. Imagine that somebody tells you he has met a smart person, and you wonder if this person is male or female. So basically we want to find the probability of meeting a male given that this person is smart. So basically this information that we have is given, so this is why I put it on the right hand side. and we will want to find this probability. Of course, we need some information to calculate this probability. The first information is the initial assumption on the population of the male and female. So this is basically the first one is the initial assumption. So when we don't have any information, then the neutral assumption is to give the same probability to male and female. Okay, so this is why I put it half here. The next information that we have is some new information that somebody gives us. Okay, so this new information basically is these two conditional probability. Okay, so basically somebody tells us that, okay, the probability of finding a smart person given that this person is male is 0.2. Another new information is the probability of finding a smart person given that this person is female is 0.5. So this is the new information. So based on this new information, then we want to update our initial assumption or the old data that we have. Okay, so the only part that is still missing is the evidence part. This P smart, the probability of finding a smart person. Basically, this is evidence. The denominator of the Bayes theorem. And basically how we can find this basically we can write P smart equals to the probability of a smart given male multiplied by the probability of male plus P smart given female multiplied by P female. So this law or this rule, we call it marginalization. So this is marginalization, or also we call this the law of total probability. Law of total probability. So this law of total probability mathematically reads as, so the probability of A equals to the sum of the conditional probability of A given B, so Bn, multiplied by P Bn, sum over all the possible events of Bn. Okay, so this is the law of total probability, and based on this then we can calculate our evidence or P smart. So we have all the parts in the Bayes theorem, then let's calculate the probability. So basically this is the new information that we have. This is the prior probability or the initial assumption, and this is the evidence that we have just calculated. So this is the new information and this is initial information, and basically we can calculate this as putting just the probability, and then finally find the probability of a male given a smart equal to 0.29. So then you see that by knowing that the person is smart, now the probability of being male goes from 0.5 to 0.29. So basically this was our initial assumption, no? P male, it was our initial assumption. Now it is updated to given that a smart. So by knowing that the person is smart, you see that the probability of being male changed from 0.5 to 0.29. So this is an updating of the information based on the new information that we have. And this is an example of Bayes theorem for information updating. Let me give you another example on information updating using Bayes theorem. Assume that you have two bags of steel bolts. The bolts are of same size and shape, so in principle you cannot distinguish the bolts. And those in one bag were made in Spain, while the others were made in Germany. So the technical specifications state that under a standard traction test, the probability of collapse of a Spanish bolt is 0.1, while the same probability for a German bolt is 0.4. So initially, we don't know which bag contains the bolts made in Germany and which bag contains the bolt made in Spain. So our goal is to identify the bags, okay? So for this, you take one bag and perform tests to 3 bolts inside that bag, okay? So you select 3 bolts from one bag and then you perform experiments. So in each experiment, of course, you have 2 possibilities. Either the bolt collapses or not, okay? And you do these 3 experiments, and the outcome is the following. In the first experiment, the bolt doesn't collapse. In the second experiment, the bolt collapses. And in the third experiment, you don't see any collapse of the bolt. So basically, these 3 information are new information that you obtain from experiments. Now you want to identify the bags, or basically you want to calculate the probability of a bag being German or contains the bolts made in Germany. So in the next slides, I will present how we can solve this example. So let's solve this problem using information updating based on Bayes theorem. Here we also use probability tree to help us calculate the probabilities in the Bayes theorem. So initially we start from some assumption. So the neutral option, when we don't have any information about the bags, is to give equal probabilities to both Spanish and German bag. So here you see that this is our initial assumption, or we call it also prior in the Bayes theory. So having these equal probabilities, then we want to update this assumption using our new information, which is the first experiment. So what this experiment tells us is that the first bolt that we choose didn't collapse, okay? So here our goal is to calculate the probability of this bag being German, so PA. So initially we assume 0.5, same as the Spanish bag. So basically this is PA, the prior or the initial assumption. So how we can update this initial assumption is to use Bayes theorem. So here you see at the below, I rewrite the Bayes theorem. So this is the initial information or assumption, let's say information or prior, which is 0.5. Then considering that this bag is German, we know that the bolt didn't collapse. So basically we can write this probability P. So the first experiment, so the event of collapse or no collapse, we call it B. So PB which in this case the first experiment didn't collapse, given that the bag is German. Okay, so this is the conditional probability. So if you remember, in the last slide, we give some instructions. So the instructions tells us that the probability of a German bolt that without collapse is 0.6. Okay, so this is the information according to the instructions. And then now we can have this conditional probability. So on the second branch of the tree here, all of these values are conditional probabilities. And using this information, then we can update our information. So this is basically in the Bayes theorem, PB given A is the new information. So here is 0.6. Okay. So the only thing that remains is the evidence, PB. This is the evidence. And basically this evidence can be obtained by these right hand side numbers on the tree. So basically this right hand side numbers is obtained by multiplying this conditional probability by the initial assumptions. For example, in the case of the no collapse in the German bag, we can multiply this conditional probability to the prior assumption. So multiplying these two gives us this. So basically this is PBA and PA, the conditional probability multiplied by the prior assumption. In the case of the Spanish bag, also you can do the same. You multiply the initial or prior assumption, multiply by the conditional probability. This is again according to the instruction, and then you get this 0.45. So in general, the total probability of no collapse is the sum of these two, 0.3 plus 0.45. So this is equal to PB, which is the probability of no collapse in this case. So in this way, you can calculate the evidence, which is PB. And then this evidence is 0.75 as the sum of the two values in the right hand side of the tree. So now you have all the terms, 0.6 in new information, 0.5 the prior, and 0.75 as the evidence. And then the updated information becomes 0.4. So this is basically the probability of selecting a German bag given that the first experiment is no collapse. So you see that using the new information, then you can update our initial assumption 0.5 to 0.4. So the initial assumption of the bag is German now decreases to 0.4. So this is because the first experiment didn't collapse, and based on this new information, the probability of selecting this bag as the German one decreases. Let us update our information using the second experiment. So here again we plot the probability tree to help us calculate different probability terms in Bayes theorem. Note that here in the first branch the probabilities are not equal because we have already updated this value using the first experiment. So basically here is the probability of the German bag equals to 0.4. Initially it was 0.5, but with the first experiment we updated to 0.4. So basically here this information are from the previous experiment. So this is again we call it prior. So every time that we call prior, it means that something from the previous or the old data. So we want to update this prior using the second experiment. So in the second experiment, the bolt that we choose from the bag collapses. Okay, so using this information, then let's calculate the posterior or the updated information. So here again, PA, the probability of the bag being German, is 0.4. Okay, so this is from the previous or prior experiment. And the conditional probability of the event, basically the collapse event, you can obtain it from the second branch. So here you see these values are again conditional, same as before, nothing changed, conditional, because these values are coming from the instruction. So it is always the same. So here we have to choose the probability of the collapse, the second experiment collapse, considering that the bag is German. PB condition to A, which is this value 0.4. This is according to the instruction. So we have these two terms in the, if you look at the Bayes formula, so this PB condition to A now is 0.4 from the instruction, and the prior from the first experiment is 0.4. So the only remaining term is the evidence, which is again coming from the right hand side numbers on the tree. So these numbers change because the prior probabilities change, and we have to update this information also in the tree. So you see that these values changes with respect to the previous tree. So here we are considering the probability of collapse. So we have to sum this value, which is the collapse in the German bag, and the collapse in the Spanish bag, 0.06. So if we sum these two values, then we come up with the PB, which is the total probability of the collapse, which is basically is 0.22. Okay, so having these values, then we put all of them in the formula, and then we come up with the posterior probability of 0.73. So this is posterior. And now you see that using the new information of the second experiment, the probability of the bag being German increases from 0.4 to 0.73. So this is the second update of our information. We can further update our information using the third experiment, and we leave this exercise for you, so please do it at home and we will discuss it during the class. Another exercise for you is to incorporate all these three experiments in just one shot, and for this problem you will have a probability tree like this. So the event here you can consider as the 0, 1, 2 and 3 collapses. You see that in the probability tree, the conditional probabilities that you have to compute here have basically more branches. So instead of 2, you have 4 branches for each bag. So for calculating these probabilities, another hint is to use binomial distribution. So after calculating these probabilities using binomial distribution, then you can find the marginal probabilities on the right hand side of the tree. So having all these probabilities, then you can obtain the updated information having all the 3 experiments outcomes. So you have 3 experiments, and using the information of these experiments and in just one shot or using one probability tree you can obtain the probability of the bag being German after finishing 3 experiments. So basically you should get the same result that you get in the first exercise. So in the first exercise you update the information using the third experiment, but you can do all this updating in just one shot and using one tree, which is this tree. Okay, so but the result should be the same. So we will discuss these exercises during the class.